right, we're streaming, we're screen sharing, we're Zooming, we're doing everything. Welcome back, everybody. Happy Tuesday. So in terms of our schedule, we're right on pace here to go over formative assessment that was due yesterday. Thank you, everyone, for completing it. Well done. I've updated your grades accordingly, so now you're 4 for 4 on quiz points. We have stuff to talk about today, stuff to talk about next time, and note that I have 3 additional downloads for Thursday to give us an opportunity to see this same material in another context. So grab those whenever you get a chance, and then later this week I'll have next week's material up. You also have homework 2 that is available for you to work on. That is due a week from tomorrow. Are there any questions about that yet? And if you haven't even opened it yet, that is totally fine. But I'm going to ask each class period no matter what. So, any questions yet on homework 2 that I can answer? Not yet. Okay. Then what we can do to start with today is talk about our formative assessment. So I have set this up so that you can have multiple entries. So if you'd like to take notes as we go to sort of answer the questions again, you're welcome to do that. I've already went through and graded it to make sure that everybody did so, and I looked at your answers to see how folks were doing with this. So first question then, what is the difference between a mean and a standard deviation? What did you write down?
The mean is the arithmetic average, and then the standard deviation is the average deviation from each person's value in the variable sample mean.
Yes, those definitions are exactly correct. The mean is the arithmetic average. Standard deviation is the average distance of each observation from the sample mean. Now, if you were going to tell me that, answer that same question and you're explaining it to, say, your grandma or a 5-year-old, right? My mom has no idea what I do for a living. She knows that I teach college, and that's it. So if I was going to explain this to my mom, what would we say? What are sort of the bigger picture ideas that the mean and standard deviation go with? What are they telling you about a quantitative variable? Middle. I'll take gestures. Middleness. 2 words.
Added everything up and divided.
We'll do mean first. So mean is an estimate of middleness. 2-word phrase that goes with middleness. Starts with a C. Central tendency. Yeah, so the mean is one way of indicating sort of middleness. It's the arithmetic average as opposed to the exact middle, which is the median, or the mode, which is most frequent. Standard deviation, why do we want to know standard deviation? What does that tell us about? Variation. Standard deviation is the square root of variance, so I'll take that, yes. More generally, what is it the same thing as the mean, related to, or completely different? It's related or completely different depending on your answer, but it's not the same. So you said related, Jose. What do you mean by that?
Proportionally related to how dispersed it is from the central tendency.
Yes. Oftenest from central tendency, yes. How dispersed it is. Dispersion is the key idea. So if I told you that the average age of my children was 9, does that tell you about our household? No. Right? Because that could be, I have a 8-year-old and a 10-year-old, which is the case of my nieces. So they wear the same clothes, they fight over the same things, right? They're very close. Or, as it actually stands, I have a stepdaughter who's 13 and a son who's 5. The average age is 9 in both of those. But it's a very different experience trying to parent a 13-year-old and a 5-year-old than an 8-year-old and a 10-year-old, right? So I would say that standard deviation or variance is related to the mean in that it's how far off from the mean is how we define it, but it's separate in the sense that it describes the extent of variability around that middleness. Like, is middle really typical, or is it not as typical, I guess, in the sense of 8 versus 10 versus 5 versus 13? So does that make sense? Do you have comments, thoughts? So you want to know both of those things, basically, to try and summarize a variable. The third thing that doesn't show up in modeling but shows up in description, of course, skewness or asymmetry or one-sidedness. Symbols. How do we denote a mean in a sample? Y bar, or if you're writing a manuscript, what's your other option? Capital M, yep. How about in the population? Mu, that's the U looking thing. So it's a Greek letter mu, MU. How about standard deviation in the sample? That's an S. In a manuscript? SD, yep. I've also seen variance instead. I usually do that as like capital letters VAR. That one is a little tricky because in the programs, as you can see, var sometimes stands for variable and sometimes it stands for variance. It's context specific, but SD is sort of universally standard deviation. We have a question or something from the Zoomers? Come on. Oh, one got booted by her internet. Okay, welcome back, Amanda. Yeah, that happens, right? The internet decides to boot you and then all of a sudden you're missing your class. Population standard deviation, what's the symbol? It's a circle-looking thing. Yeah, it's sigma. It's lowercase sigma. That's population standard deviation. When we get into models, you'll see sigma squares used for variance almost exclusively. So that one will show up repeatedly. Okay, so any questions or comments on number 1? Okay, next one. What 2 elements go into determining the standard error of a sample mean? Standard deviation is 1. Sample size, yes. More specifically, the square root of sample size. And by the way, I went tracking down whether it's n or n minus 1, again, for the standard error, because n minus 1 looks correct to me, but all the places that I saw it was n, and so I was like, okay, I need to check this out. It's n. The definitive answer is n. And do you know how I figured that out? Check the math that SAS and Stata was doing. If they use n, then I trust n. The reason that it looks different to me is because later on when we have standard errors of other things besides means, those reflect the amount of degrees of freedom in the model, denominator degrees of freedom, so it does subtract the mean. But the logic behind why it's n is that you've already lost 1 point in terms of having to calculate the mean to get the standard deviation. You don't have to calculate anything else because you know the sample size. So to do n minus 1 would like hit you twice, whereas there's only one thing. So standard error is square root of n. That's on the bottom, which means does more people or fewer people give you a smaller standard error? More people give you smaller standard error, more precision, less wiggliness around the population mean. Likewise, if we have standard deviation of the sample in there, is it more standard deviation or less standard deviation leads to smaller standard error? Yeah, less, yes, exactly. The less variability around the mean, the more precision the mean estimate has. So yeah, that leads into the next one. Difference between standard deviation and standard error. They're related to each other, right? But the level of abstraction is different. So what did you guys write down? Yes, standard deviation is within a sample. It's the average distance of any given observation from the sample mean. So the can within the 12-pack sort of idea. So then standard error, which is standard deviation divided by square root of n, what's that tell us? And so here there was some variability in the answers people gave, so I want to make sure that we cover this specifically. What does standard error tell us? Standard error of the mean.
It's the average deviation of what we can expect a person to be from the population.
Not a person, the sample mean. Yeah, so it's a higher level of abstraction. It characterizes the average distance of a sample mean from the population mean. So there's no more people at that point. So it tells us not necessarily the accuracy of the population mean, it tells us how wiggly the sample means are around the population mean. I'm saying wiggly because I don't want to say variance to be confusing, but it's sort of like noisiness, if you will. If you think of a factory that's spitting out, cans of Mountain Dew and 12 packs of Mountain Dew, you want to make sure that the average amount of liquid in each of those cans, and by extension, each of those 12 packs, is the same, right? You want no wiggle, you want consistency. That would translate into a very small standard error. Whereas if you have a factory that doesn't have a good rate of consistency, then you'd have a lot more wiggliness in what any one can and thus any one pack's mean would have. So it's a level of precision. In addition to sample means, every other statistic that we'll see is going to have standard errors as well. So every time you want to know if you have, say, a relationship, and the best guess of your relationship is this number, you want to know how wiggly that number is, how certain you are that it's that number and that you get that number over and over and over again. That's what standard error is telling you, is precision, imprecision, more specifically. Question?
When they do a political poll and they say there's an error of plus or minus 5%, standard error?
Yes, it is. You'd have to see whether the error, sometimes they report 2 standard errors instead of 1. But yeah, if you see the plus or minus, however many, they're telling you standard error. And that's just as important because it tells you whether or not, if you have, say, a 5-point difference between candidates, but the standard error is 5, right, that's not a difference. 2 standard errors around an estimate gives you the confidence interval, roughly. 2-ish, depending on your degrees of freedom. So if you had a difference of 5, is that really different than 0? Well, if you have a standard error of 5, that difference of 5 could be anywhere from -5 to +15, 2 standard errors. If you had a standard error of 1, that difference of 5 could be anywhere from 3 to 7. So it's your confidence, essentially. It's more standard error is less confidence in that size. Yes. One of the reasons why I don't care what GRE scores are for applicants. No, I'm dead serious. I don't even look at them. Do you know why? They don't report standard errors when you get your GRE scores. They actually have them in a manual that's buried online. And I did a presentation to our undergraduates in psychology when they switched the GRE scale from the 500 mean to the 150 mean. So when they had it on a 500 scale, that was the average. It went from about 300 to 800. The standard error at a quantitative GRE score of 550 was 50 points. So that meant a score of 550 could really be anywhere from 450 to 650, which is the entire range of the applicant pool, right? So when you have that amount of noise, it's hard to take it seriously. Instead, what I look at, their letter. Is it grammatically correct? Number one. Do they know what they want? Is it specific? Is it goal-directed? Does it explain why they have the experience that prepares them adequately for this? That is way more important than test scores. So, off my soapbox, but just saying, standard error is super important in real life. Because just knowing the difference without knowing the margin of error doesn't tell you anything about whether you should believe the difference. It's surprising how many high-stakes scores are given without standard error attached. Like, I took the ACT to go to college. Some of you probably took that if you lived in the Midwest. Otherwise, it's the SAT. I didn't get a standard error. I have no idea what it is. So, what I do know is that the score was different every time I took it. So the question is, was that expected variability or unexpected variability? Who knows? It's confounded with, in theory, the amount of extra knowledge I had as I took it later. So,
IQ also have a standard error?
what does?
IQ?
Everything does. That's a whole nother set of courses that you can take in terms of how you interpret, trust, and make decisions about scores from tests, what goes into establishing reliability for those scores, validity for those scores, the statistical models that underlie the scores. That's psychometrics. That's a class I'm teaching in the fall, by the way, factor analysis and structural equation modeling. So yeah, standard errors for everything. I got it off on a tangent. Okay, are we good with this one? Okay. And I'm on placebo too. I've only had my coffee this morning. So, difference between a linear transformation and a nonlinear transformation.
Linear transformation changes the variable value changes evenly, and then the non-linear, like are uneven, the variable values.
So yeah, linear means evenly. Nonlinear means unevenly. Now I think, was it Dre? You asked me, why would you do this for nonlinear? Was that you? Okay, I thought it was you, but I could be misattributing. Was that you? No? So when would you do this? Linear transformations happen all the time, particularly for predictors, so that you can put them on the same scale. That's why. So for instance, if you make a z-score transformation, you are changing the scale of a variable to have a mean of 0 and a variance or standard deviation of 1. Since the square root of 1 is 1, you can say either way. That way, if I tell you I have a z-score of 3, that means I am 3 standard deviations above the mean. That's pretty extreme, whereas if I have a z-score, say, of 0.5, that's well within sort of expected territory. When would you do nonlinear transformations? These will show up far less frequently, but they are used in models to predict categorical outcomes and outcomes that have boundaries to try and they make it so that you can predict an outcome that does not have those same boundaries. Nonlinear transformations remind me of the mirrors at the Children's Museum at the mall. Have any of you been to the Children's Museum at the mall before? No? Oh, you're missing out. It's 2 floors of chaos. But they have, outside the art room on the first floor, they have like funhouse mirrors. Like they're distorted. And they're hilarious, right? Because you step in front of them and all of a sudden your legs are like, 10 feet long and your torso's like this. And that's a non-linear transformation, right? Pieces are distorted. You're not transformed evenly as opposed to a regular mirror. Or a mirror in the dressing room, in which case you are transformed evenly to look like crap, all the way down from head to toe. Fluorescent lighting does no one any favors. You will see an example of that, if not today, then next time for a nonlinear transformation when we talk about correlation coefficients and confidence intervals for them. That's one time you will see it. But sometimes if you are concerned about the skewness of a variable, if you do a log transformation or a square root transformation, those are both nonlinear transformations that will take the skewness and sort of shove it back towards the middle. So you'll see those in that context as well. All right, I think that was all the questions. Do you have questions about any of this? Question?
I just don't really know why it's desirable to have a nonlinear transformation.
It depends on your perspective. The 2 instances in which you would see it, one is if you are trying to make a variable look like something else in order to use a technique that requires it to look like that. So for instance, a lot of the models assume conditional normality, that your outcome has some kind of normal distribution after you're done predicting it. If you have a skewed outcome, that may not be the case. But if you do a nonlinear transformation to reel that tail back in towards the middle, it looks more normal, and thus the results of that technique would be more believable. That's one instance.
So are we hiding results?
It ends up that you are changing the type of model that you're fitting in that case. I'm getting ahead of myself, but if you think about a line, a slope that's relating a predictor to an outcome, it's not a straight line in that case, it's an exponential curve, it's a bendy line. And so if you're okay with it being bendy, then that's fine. But it's an empirical question whether straight or bendy works better. But that's one instance in which you'll see nonlinear transformations is to make variables better behaved, so to speak, in terms of the techniques. You don't have to do that. A better option would be to pick a whole different kind of model. But once you, we'll start with one kind of models, and then that's actually the follow-up class to that you can take. The other is when you're trying to predict something that's bounded and you need to change it so that it's unbounded. That one is easier to explain with an example. All right, other questions? All right, then I will shut this much down. Last time we were talking talking about this stuff, confidence intervals, one sample T and Z tests, and expected versus unexpected. Remember this? So one of the things that we can do if we have a sample mean is ask how it compares to some hypothesized value, such as a population mean. That's an example of a research technique in terms of a univariate statistic. That's all we've got so far. And so we saw how to make a confidence interval that describes the expected variation around that estimate for the sample mean that we got, where we would have the estimate plus or minus some sort of critical value that gives your level of confidence. So if you want your interval to contain 90% of the replications, that's a 90% confidence interval. 10% would be outside, that would be your alpha. Aberrant, outside, unexpected is alpha. More typical than 90% is 95%. And so the standard error times this value for T critical here is going to be roughly 2 in most cases. That gives you your interval around this. You can then take that interval and turn it on its head to try to figure out whether or not that mean is different than a population mean by mapping it onto where it falls on the T distribution. So we did an example doing this. So let's go back to example 2, how to do this sort of thing in software. We were looking at page 4, which was an example of how to test a sample mean against some targeted value. And the example that I'm using right here is a subsample of the general social survey data. These are years of education, which we're treating as a quantitative variable. And I'm asking SAS, in using proc t-test, or Stata using just t-test, to answer the question, if the true mean were 12 for years of education, how likely is it that I'd see a sample mean of what we got? That's the question. So we get all of the information that we need to answer that question here and here. The sample mean in this case is 13.8. Standard deviation, the average distance of each case relative to that sample mean is 3.2. Given our sample size of 100, that translates into a standard error of, so standard deviation divided by square root of sample size gives you this number right here. That describes the wiggliness of the sample mean relative to the population mean. If we take that sample mean, subtract from it what it's supposed to be, which is 12, and divide by the standard error, that gives us our T statistic right here. So what does that mean? T is a scale where the middle is 0 and the absolute value moving away from 0 indicates how unlikely it is to find what you found in your sample given what you expected. So the T distribution looks like this, where it's shaped slightly differently depending on how many people you have. It's flatter the fewer people that you have. So we have a question from the Zoomers. Let me pull that up. If Zoomed mute, their mic won't hear your background noise. Oh, okay. All right, yes, note to the Zoomers to please mute, that way the background noise is not on there. Okay, but I shouldn't mute, otherwise we lose the purpose. So we have, let's see here, a T of 5. Now where is that on this picture? Gestures, please. Yeah, this way, all the way to the right. It's not even in the picture. In other words, if the true mean were 12, the frequency with which we would observe a sample mean of 13, given our standard error. So the standard error is basically how many standard errors out are we? We're like 5 out. We're well into unexpected territory. Very infrequent. And the probability of observing a sample mean that extreme, if the true mean were 12, is less than 0.001. So really unlikely. The interval around the mean does not include the 12. So if we redid this study over and over and over and over again, the population mean is supposed to be in there 95% of the time. Ours is nowhere near that, so it's really unexpected. Same thing in Stata. Information shows up slightly reorganized, but it's the same question. Do you remember this part right here? The 3 different p-values? When we're deciding what is expected versus unexpected, we're talking about one-tailed test or two-tailed test and making that call. Remember this? Two-tailed is if you are willing to say unexpected too high or unexpected too low. One-tail is if you're willing to call your shot in advance, so to speak, and claim either too low or too high. The latter, calling your shot, is not typically done. And then we have a results section describing how you would interpret that sort of finding. And I think that's where we left off. Okay. Questions? So this is for a quantitative variable. You can do the exact same thing for a binary variable. A binary variable, the mean is the proportion of cases that have a 1, whatever that means. It requires a different procedure. So this is one you've already seen, proc-freq, procedure for frequencies, and in Stata it's PR test for proportion test. And this time, I have a variable for whether or not someone is male or female. That's how it was, that is how it was collected and coded in the data set. So for better or worse, it's binary in this particular example. I have named the variable to clearly tell us who is the 0 and who is the 1. It's an arbitrary coding system. Somebody has to be 0 and somebody has to be 1. So this much you guys did in your first homework. Do you remember that? That much gives you that table that I'm staring at right here. Frequencies and percentages out of the total. Where under cumulative frequency, it tells you how many people are in your sample that answered this question. The extra part, this is asking it to test the observed proportion of 1 values against an expected proportion of 0.5. That's what it is in the population, roughly, so I wanted to see how our sample compares. What SAS does is test the proportion of zeros. So if you look at this part of the output, the proportion that it's testing is the proportion of 0 values, which is the proportion of men. It also gives us a standard error for that proportion, labeled ASE for asymptotic standard error. The reason it's labeled differently is that we don't have to calculate a standard deviation in order to get the standard error. In binary data, the standard deviation comes from the mean. It's the mean times 1 minus the mean. It gives us a confidence interval around that mean. 2 different versions. There's an exact test that is slightly different computationally, so it gives both of those. And then it also gives you a test statistic, this time using Z, because we don't need to find the standard deviation. Z of 2.2, we go back to our picture here, this one. So Z and T look the same, except T is flatter if you have fewer people. So where is a Z of 2.2? And somewhere in here, it's in the orangey red area. So that means relative to 50-50 split of males and females, our observed proportion of males of 61.61 is way high. It would not occur with very great probability if the true population were 0.5. So our sample is unexpected in that way. How unexpected is it? About 3% of the time. So not very likely that we would see a proportion of males of 0.61. So since there's 100, I can do that, but here's the percent. If the true proportion were 50.5. Okay. With me so far? Now, when would you do this in life? Can you think of a situation in which this sort of test and information would be useful? Disproportionality, you said? Can you elaborate on that?
Comparing if African American women versus white women are proportionally distributed according to a particular community.
Yeah, great answer. So yeah, if someone is questioning how representative your sample is, if you know that in the state of Iowa, this proportion of the sample has this characteristic, and you go out and collect a sample, this is one way to provide some kind of empirical evidence that your sample matches that targeted proportion or not. So it's just about the expected distribution of something versus the obtained one from your sample. And you can do that for a quantitative variable in terms of whether your mean matches the mean that it's supposed to, and you can do it for a binary variable in terms of whether your proportion matches the proportion that it's supposed to. That is the only example I can think of when you would do this, to be honest. So thank you for coming up with it. Question, Jacob?
So to run this, the p-value is the expected up toward the top, like when you're typing in the syntax. So that binomial p is the percentage that you're expecting?
Yep. What would I do if I wanted to compare it to 0.75 instead?
Just replace the 0.5 with 0.75?
Yeah. Homework question. By the way, for the transcriptionist, that was a cough homework question, not one question. Sort of an ongoing joke. I once heard of somebody who would stomp their feet. Did I tell you this? When they were saying something that would be on the test or whatever. But I can't stomp very loud in a carpeted room, so I'm just going to do a homework question. So yeah, you can change this to whatever you like. Whatever it's supposed to be is the idea here. Now, here's a little fun fact. SAS and Stata operate differently in the same command. SAS tests the observed proportion of 0 values against what you tell it to here. Stata does the opposite. It tests the proportion of 1 values. Now, if the proportion you're testing against is 50-50, then this doesn't matter. Because the z-score that goes with the proportion of females is exactly the opposite of the z-score that goes with the proportion of males. It's minus 2.2. If we go back to our table, that just disappeared. Come on, there we go. So minus 2.2 is just as far away in terms of into unexpected territory. That means we have fewer females than would be expected. We have 39% instead of 50%. Or we have more males at 61% than we have expected at 50%. Now, what if you want the other one? And you'll have to do this on your homework as well. Recode the data. So here's a little snippet of results, how I would describe this data output for the proportion of ones. If you want to flip it so that you can get the other one that's not provided by your software, we have to create a new variable in the data set in which we switch who's the 0 and who's the 1. So here's how we do this. First in SAS, this first thing here, data set, in SAS, that tells it which data set you want to do transformations in. Data means make me a new data set, put it in the work library, call it example 2. Set means from the existing data set in the work library called example 2. In other words, save as itself. Right into that same data set. First thing I'm doing is making a brand new variable. I named it female 0, male 1 because that's what it's going to mean. And I am setting it equal to a dot. A dot is a missing value. So I'm creating a column with the name female 0, male 1 that's empty. I am then going to tell it to put values in that column using conditional logic. If and then are SAS commands, that's why they're in blue. So what I'm saying is if the old variable was 0, take the new variable and make it 1. If the old variable was 1, take the new variable and make it 0. Again, why am I doing this? Because SAS gives you a proportion test against the 0 values. If you want a proportion test against the 1 values, you have to turn the 1 into a 0. It's just flipping the coding. So now, rather than testing the 61%, it's testing the 39%. And the output matches what we got in Stata because Stata tests the 1. The Stata code to do this same thing looks similar, although it is logically backwards. So there is no data set analog because in Stata you're working with one data set at a time, and so it assumes that's the one you want to do things to. Gen means make me a new variable. The name of the variable is right here, and set it equal to a dot. So that part's the same. I'm taking a new column, naming it female 0, male 1, and setting it equal to empty values. Then, this is replace the new variable to be 1 if the old variable equal 0. So it's setting up an equality condition, not assigning a value. So it's logically backwards because SAS says if the old one is 0, make the new one 1. Stata says make the new one 1 if the old one is 0. Same idea, just a slight rearrangement of the syntax. And then make the new one 0 if the old one is equal to 1. And then we can do PR test on the other one. Then you get the exact opposite output from before, where now Stata is testing the old 0 values instead of the 1s.
Would that ever get confusing with the
Yes.
variable names still being the same? Since you switched the value from
So I translated the variable names to be, it used to be male 0, female 1 was the name. I renamed it female 0, male 1 to try and avoid that problem.
oh, I see.
So the name
I was
contains
just
who the
looking at the
0.
number.
Yeah,
Okay.
because exactly this. The old variable in this data set as it came to me, it was a variable called female. And that means that the name of the variable and one of the categories were identical, which is really tricky. So I was erring on the side of trying to be overly explicit here so that when you get a piece of output like this that has 0s and 1s, you know who's the 0, female is the 0 in this case, and male is the 1. So this is the analog to what we just did with the mean for a proportion instead of a quantitative variable.
Sorry, I have another question.
Please.
Just above that, back to the syntax.
Yep.
It says, like, there's the if line, then if, then it says format, male 0, female 1. Why does it say F female? Is that a typo or is that on purpose?
That is on purpose. This thing right here is a format. It is an instruction that I already created back here to have these labels show up on your output. So in my case, I apparently didn't run it after I formatted it. I had the code from the output from before. But this is another way to make it less confusing, is to apply this labeling system. So F female in my naming conventions means the format for female male, as opposed to the format for male female. And so this is just a piece of information that then gets tied to the column, so that in theory it spits out 0 female instead of 0 to make it unique. It labels it, exactly. It's the analog of value labels in SPSS. And Stata has the same thing. So I will, back to where I was, I will add that to the handout and fix it for you. So this would actually be like that if you run that code properly. That's what it would look like. Thank you for the question. Okay, other questions? Yeah, and then here's the Stata output that goes with it. And there's that. Okay. Are you ready to see something more useful? Yeah. Please, exactly. From univariate to bivariate. Let's go there. Slide 20, lecture 2. So everything we've talked about so far is describing one variable at a time. Its central tendency, its dispersion, possibly its skewness. But most research questions involve relationships between variables. Does this variable x predict another outcome y? As x goes up, is y likely to go up also, or does it go down? These kinds of questions. So questions involving relationships between two variables, this is known as bivariate association, where bi means two, like in bicycle, not like in bisect, split. The type of bivariate association that you need depends on what kind of variables you're trying to associate. So we will see first associations among two quantitative variables, and then we'll see other permutations. So each of these is going to have what's known as a point estimate. That is the index of their relationship. And it's also going to get a test to establish its statistical significance. Basically, if there were no relationship in reality, in the population, what are the chances that we would see a relationship of the size we observed? If it's well into unexpected territory, we declare it significant. More formally, this process of asking how likely our result is if there really was no relationship in the population is what's known as null hypothesis significance testing. We're also going to see how to get standard errors and confidence intervals around these measures of association. And each of these I want to do in the context of what the association would mean and when you would use it. So the first one, something called Pearson's correlation. Ta-da! Have you heard of this guy before? Yeah. So colloquially, if you know, if you think the word correlation, what do you think of? Connection, yeah. Association, relationship. Correlation is a word that people understand sort of intuitively. There are kinds of them. One kind is what's known as Pearson's correlation. This is a value that describes the extent of linear relationship between two quantitative variables. So it's most easiest to depict this using a new type of plot called a scatter plot. In these scatter plots down here, one of the variables is along the x-axis and the other variable is along the y-axis. So each of these dots represents a coordinate of where it is on x and where it is on y. The correlation in the population is denoted often as this thing right here, this p-looking thing. That's rho. It's a Greek letter. In the sample, it's known as R. Correlations as a metric range continuously from -1 to 1, where 0 means no relationship whatsoever. So here are some examples of correlations. So if we start on the bottom left here, if you had a set of dots that look like this in a scatter plot, the XY coordinates, this depicts a perfect positive correlation because as X goes up, Y goes up, always. Higher X's go with higher Y's. These ones here depict a correlation somewhere between perfectly positive 1 and 0, meaning no relationship, where we have something that's strong. As X goes up, Y goes up, but it's not lockstep. A weaker one here, as the third picture in, there's a tendency for Y to be higher if X is higher, but again, it's not lockstep, it's even weaker. In the middle here, R equals 0, no relationship. If I know what your value is on X, I have no idea what your value is on Y. They're unrelated to each other. A correlation of 0 is depicted in a scatter plot basically as just a circle of points. Then we go the other way. We head into negative correlations, where these are the opposite pattern of relationship. So a negative correlation, so there's a weak one, a strong one, and a perfect one here, means that as X goes up, Y goes down. In terms of the strength of these relationships, what we care about is the absolute value of R. So a correlation of 0.8 is just as strong as a correlation of negative 0.8. The sign tells you which way it goes. If higher values go with higher values, or if higher values go with lower values. With me so far? All right, so how do I get one of these? I'll show you the math, and then I'll show you how to do it in software. First thing we need is the mean and the variance of each of our two variables. So because I'm talking about X and Y, I'm labeling these things slightly different. So the mean of X is X bar. By the way, I think, Cheryl, you had a question about how to get the bar on there. I don't know how to do it in the typing, but you can hunt into the equation editor and look for accent marks, and one of them will be a bar.
Okay.
There's all sorts of, there's dots that can go over them, triangles that go over them, all kinds of things. One of them will be a bar somewhere in there.
Okay.
And apparently if you have a laptop where you can touch the screen, I think you were saying you can make a bar sign and it will figure out what you meant. So yeah. So we need the mean for X and the mean for Y. Then we need the variance for X and the variance for Y. And so note the change in the notation here. S is standard deviation, S squared is variance. The subscript tells you what variable it is the variance of. So it's more clear to say this is S squared for X specifically, since there's two variables that we're talking about here. One is X, one is Y. So we have the middle part here in variance. That's how far off each observation is from the mean for that variable, whether it's X bar or Y bar. We square those offnesses. Do you remember why we do that? Get rid of the negative, so the negatives and positives don't cancel each other out. So it's the difference squared, then summed over people, divide by n minus 1. We lost 1 degree of freedom because we had to calculate the mean in order to do this. So those two we know already. The next one, next step, is new. It's a quantity that is known as covariance. Varying together, like codependency. Cooperation, can I say that one? Co, meaning together. This one is how far off the mean you are on each variable multiplied together. That's covariance. So whether you're above the mean or below the mean on X times how far above the mean or below the mean you are on Y. So if you have a relationship between X and Y that's positive, if people who are above the mean on X tend to be above the mean on Y, the sum of these things is going to be a positive number. if you have no relationship, sometimes if you're above the mean on X, you're above the mean on Y, but not always, this will be 0. And if people who tend to be above the mean on X tend to be below the mean on Y, it'll be a negative number. And it's n minus 1 because within variables we've only spent 1 degree of freedom so far. Bit of trivia, a covariance of a variable with itself, by the way, is variance. So you'll see that sometimes in output in correlation matrices. So the thing about covariance is that it's necessary but not sufficient to tell us about a relationship. So for example, if I look at the relationship between height and weight in 10 men, just made up some data. I have height in inches. On average, they're about 6 feet tall. The standard deviation is 6 inches, so the average distance from the mean in this sample is 6 inches. The variance, then 6.5 squared is 4.2, and here's the range 82 inches. Then I have weight in pounds. On average, about 236 pounds. 20 pounds off on average in terms of the standard deviation, there's that. If I plug in these values to get the mean, the variance, and get the covariance right here, I end up with something that is 135.24. That metric, what it's 135 of, is inch pounds. What the hell is an inch pound? So I have 135. The fact that it's a positive number tells me that people who are taller tend to be heavier, or people who are heavier tend to be taller, whatever way you want to go. But it doesn't tell me how much. It's 135. And if I were measuring in feet, it would be feet pounds. And if I were measuring in kilograms, it would be inch kilograms. And the number would be different, and I would still be saying, what the hell is that? So because of what the hell is that, we have to convert that number into something that we know what it means. That's R. That's a correlation. Correlation is covariance, inch pounds, that has been rescaled by the standard deviation of each variable. The standard deviation of inches times the standard deviation of pounds. So that, in this case, translates to an R of 0.99. So that means almost perfectly related. People who are taller than average are heavier than average. It's almost a 1-to-1 correspondence. If I found out that this R were 0.1, what would that tell me instead? Very weak association. Very weak association in which direction? Positive, meaning taller people tend to be
somewhat heavier.
Yeah, a little heavier-ish.
Sometimes.
Yeah, sometimes, a little bit, somewhat. Any of those qualifiers to take weak, right? If I found out that it was negative 0.5, then what?
Then as you get taller, you get lighter about half the time?
I wouldn't say half the time, but it's a medium-sized relationship, yeah.
Okay.
But taller people are lighter people. That's what a negative relationship would mean. So this thing, covariance, that's going to show up in advanced stats classes because it characterizes the relationship between variables and the original scales. To make use of it, though, correlation is the way more intuitive way to think about it. It's a standardized measure where you don't have to know what the scale is. It doesn't matter if it's inch pounds or feet kilograms. A correlation is a correlation. It ranges from -1 to 1. There is an adjusted version that Reviewer 3 may ask you for someday. Here is a slide for that. I have never once been asked for this. But there is a version that is adjusted for sample size because the fewer points you have, the more likely you are to find a strong relationship. So the adjusted version takes sample size into account. If I did the adjusted formula for our example, it would be 0.993 instead of 0.994. Exactly. You can't pay me to care about this. I'm sorry. It's close enough. But just in case someone asks, here it is.
Who or what is Reviewer 3?
It's sort of a meme. historically, reviewers, and I can tell you as an editor, the number of the reviewer you are is the person who got asked first. It's sort of like who they thought would be the most, whose feedback was the most necessary. And it seems like reviewer 3 is the one that's always the hardest to please. Nowadays, a lot of journals only ask for 2 reviews, and so now it's reviewer 2. I'm part of a Facebook group that's called Reviewer 2 Must Be Stopped. It's people who vent about like unfair criticisms, or that they addressed all the comments and they rejected it anyway. Like it's sort of thing. So this is like reviewer 3 is my generic description of the picky person who wants to pick apart your stats and your sample and how do you answer this person. So every review has one. So in case someone asks for an sample size adjusted correlation, that's how you would get it instead. I will tell you how to get it in software as well. Okay. So, next question then. I have a correlation of 0.99 in my example. Is that good? Is that expected? Is it unexpected?
Seems very strong.
Seems very strong. So, first question is expected relative to what? And relative to what in this case is 0. So if the true relationship were 0, how often would you see a correlation this super strong? Not very. Now, is it significantly different than 0? Can we claim that it is in unexpected territory or not? I have to do a test, you're right. So here's your first example of null hypothesis significance testing. This requires some new words. Hypothesis is a statement about some population parameter. For instance, my sample proportion of females and males should be 50-50. My mean for years of education should be 12. My correlation between height and weight should be 0, right? Some statement about what is expected. The null hypothesis is what is expected. It doesn't have to be 0. So in the example of a twinning effect in language, the null hypothesis is that their performance on these standardized tests should equal a mean of 100 because that's what the test manual said it should be. That's the population mean. And what we're doing right now, we're testing against a null hypothesis of a correlation of 0, meaning there's no relationship. So a null hypothesis is just a statement of expectation. When we're talking about associations, it's almost always phrased as the association is 0 as the null. It doesn't have to be. An example of when it might be something else is if you are adding to a body of literature that's already pretty big. Let's say that you are looking at the correlation between height and weight, and you do a meta-analysis. You know what meta-analysis is? It's a mathematical way of combining the results of different studies to try and figure out like what the average level of relationship is. Let's say that your meta-analysis finds that you have a correlation between height and weight of 0.5. It might be of interest to you to see if your correlation is different than 0.5, not if it's different than 0. So you get to pick what is expected in this case. That's the null hypothesis. The alternative hypothesis is in a statement that contradicts the null. And so this is where we have to phrase it as either different than, greater than, or less than. Different than is this equal sign with a slash through it, not equal to.
Two-tailed.
Two-tailed, exactly. Different than high or different than low, we will take. Next step, choose a distribution. Our friend T, because we're testing one thing right now. It's 2 sides or 1 side, we're picking 2 sides. Now, where do we want to draw the line at expected versus unexpected? So if we do traditional, alpha, 0.05. So 95% is expected. Something outside of that on either is 5% of the time. So then we have 2 decisions that we can make. If the test statistic, like the t-value, exceeds the critical value, if it's past the point of unexpected, then we say that we reject the null. It is unlikely that we would have observed what we saw in our sample if the expected thing were true. Otherwise, if our result is within expected territory, we do not reject the null. And I know that's a mouthful, but you cannot say accept the null. Someone will yell at you, not just reviewer 3, but other people too. So you can say retain the null. You can say we don't have evidence to say that we have something different.
So we can say retain.
I think you can. Other people may disagree with that.
Okay.
So there's shades of gray, but you can't say accept. To me,
No, okay.
retain and accept are not the same. But do not reject is a mouthful. So let's do it.
But can I ask a question?
Please.
Would it be improper then to say I reject the original hypothesis?
If that's the other decision. So yeah, if you reject, you can say you reject the null. You can say it is really unlikely.
But let's say it happened,
Mhm.
and you reject the original hypothesis.
Yes.
Binary
Yeah, you reject the null, which is the expected, which means it is really unlikely that we would have found what we found if that were true. I reject it. If I can't say that, then I do not reject it, meaning it's possible that it's true because we're within expected variation of that. Yep. So here's what it would look like for our correlation. Our test statistic, the thing that tells us where we are on that continuum of expected versus unexpected, T, it's the correlation itself times this thing, square root of sample size minus 2 divided by 1 minus r squared. Again, no one's memorizing any formulas, but I want to point out the thing that's in here, n. The same correlation that comes from a bigger sample is more likely to be unexpected. So how do you know if a given correlation is expected or not? Is a function of sample size and that correlation. Now we have n minus 2 because we've had to compute two things in order to do this. So if we chose an alpha of 0.05, then that t value needs to be bigger outside of plus or minus 2.3. So smaller than minus 2.3 or greater than positive 2.3, but outside of that. If we want to have an alpha of 0.01, meaning only 1% of the time we would see it, this is where unexpected lies, then it's 2.75 at this sample size. So if I plug this stuff into the data that I have, our correlation of 0.994 in the original R, adjusted by sample size, 0.993 instead, works out to a T of like 25. So even though we only have 10 people, it is super, super duper unlikely to have found a correlation of 0.99 if the true correlation were 0. And by the way, this is our friend's scientific notation. Do you remember this? Mm-hmm. E to the something means I ran out of room to print this number. Minus 0.09 means that the numbers start 9 decimal places in. So you will see it printed on your output sometimes in this type of scientific notation when the number is so small that it doesn't have room to print it. So really, really unlikely. So we reject HO. It is really unlikely that we would find a correlation of 0.99 if the true relationship were 0. Alternatively, I took the same data and I made up two random variables that have nothing in common in the population. It worked out that I have a correlation of minus 0.3 between the two of them. After adjusting for sample size, it's minus 0.125. So that works out to be a T of minus 0.3-ish and a p-value of 0.7. So this result, T of right smack in the middle, right next to 0, means you're well within expected. If the true relationship were 0, I would get a correlation of minus 0.13 with a sample size of 10, like 70% of the time. Well within expected. So I would say we do not reject the null or we retain it. It's not different than 0. We don't have enough evidence to say that it is. A note about reporting. quantities that go past 1, you should use a leading 0 when you put them in your reports. So like a t value that can go positive, negative, infinity, you would use a 0 value and then 0.3. Whereas if you're reporting an r that can't go past 1, you don't need to put the leading 0. Same thing with p-values. If you want to be consistent, you can put the leading 0 always, but the thing is not to forget it when it should be there. That's traditional APA style. Okay. How are we doing so far? We're not doing? Jacob's shaking his head.
Sorry, I think I got lost along the way.
Okay, where did you get lost? Let's go back.
Can you re-explain like that last slide?
Mhm.
What I'm lost on is where we saw that it's pretty likely to obtain that R, like with that in and stuff like that, like that whole middle part.
Mhm.
The
So this is the same sample, but it's not height and weight. It's two variables that I simulated to be unrelated to each other. So I made up the data so that I know what the right answer is supposed to be. The obtained correlation between these two fake variables is minus 0.13. So there's a very slight negative relationship that I found in the sample. The question is that really different than 0? Like it's a little bit off from 0, but not very much. So given our sample size, how confident are we about it being off from 0 or not? And so the t statistic takes that correlation and it uses sample size to convert it into a place on this distribution right here, where anything past like 2 and some change, right? That's the limits of where unexpected versus expected is, would say that it's unexpected. The t that we got back is minus 0.4-ish. So if we go back to the picture, 0 is the middle, minus 0.4 is like just over here. So yeah, if the true relationship were 0, it's pretty likely that we'd find a relationship of minus 0.13. That's not that far away from 0. We would have much greater confidence that it were far away from 0 if it were based on more people.
So what we're looking for is we can't reject the null if it's within the t critical range.
Correct. We cannot reject the null if it's within the t critical range, which is where it denotes where unexpected begins.
Okay.
The critical value is the separation point between expected and unexpected.
Okay, and sorry, now I'm forgetting. What is the p again?
P is the probability of observing a result that extreme if the true result were 0.
And that's an output that the program's producing.
It comes from the t distribution. You can get an exact p value given your sample size and that t value. And yes, the program gives it to you.
So the closer that is to 1, the more likely it is that we see that pop up.
The closer it is to 1, the more expected your result is relative to what you're testing it against, which is 0. Mm-hmm. The smaller the p value, the more unexpected it is.
Are we basing our report on the p value or the result of something else?
So you need to know two things to be able to make a report about this. Great question. The p-value comes from two pieces of information. R, the strength of the relationship in an absolute sense, and sample size, which helps lend confidence to how precise you believe that R is. And so you would report both the R value and the p value, and you would have already reported the sample size elsewhere.
Okay, so
They're
in our
both
report,
important.
We would report the 0.13 and we would report the p.715.
Yes, you would. Yep. And in the handout, I've got correlations next. Here's an example of what that would look like. So in this example, I have 94 people. I found that years of education was significantly positively related to family income in thousands. Here's my R correlation of 0.45. Here's the p-value that goes with it. So given my sample size of, I guess it's degrees of freedom is 94, sample size is 96, we would observe an R of 0.452 less than 0.01% of the time if the true R were 0. So we reject the idea that R should be 0. It's significantly different. It is significantly, it is unexpected. But this is a great question, because if you just tell me that the R is significant, that number right there, that p-value, doesn't tell you anything about the size of the relationship. Because you can have a significant R of 0.01 if you have enough people. If you run an association between variables of like 10,000 people, the tiniest little offness from 0 can be into unexpected territory. Does that help?
Yes.
Yes.
So if we're looking at results and we don't have the R reported, then we should be questioning why.
Yes. It's suspicious. More generally, R is something that's known as an effect size. It is an index of the size of the relationship that is pure. It is untainted by sample size. Significance values are effect size and sample size mixed together. Okay. Other questions? Okay, well then that makes it so we're done for today. So we'll come back next time and look at some more of this stuff. So we have other types of relationships to do, as well as software to do them in. Any questions before we adjourn? All right, then I shall see you Thursday. Let me know if you need anything before then.